Now look at this next approach. It is also called as strict alteration or turn variable. So it is like this. So we are going to have, okay, in terms of that room, I'll just explain you in terms of that room, dressing room, right? So assume that there is one dressing room, and now only one person can enter it, and it is locked, right? It is now locked. See, actually, even though it is turn variable, it is not lock variable. Actually, it will be locked. Earlier, you have seen that the lock variable is not actually a lock, isn't it? It is a kind of tag, and but here it is actually a kind of lock. And now, initially, the key there will be it is only for two people, right? Now, initially, the key will be with one person, right? And only this person can go inside it. So, as long as he has the key, the other one cannot go inside. Even if he wants to go inside or not, he will keep the key. Now what happens is, he will open the door and he will enter it and he will use it and he will come out, and again he will lock it, and now he has to give the key to the next one, right? So what I mean to say is, see this, there are two people. First, one person is going to have the key with him, this fellow, and only he can enter the room. And if he doesn't want to enter the room, still he will have the key, and he will never give the key to him unless he uses it one time, right? And now he'll use it one time, comes out, locks it, and now he'll hand over the key to the other one, right? And now he can enter the room, and even if he doesn't want to enter the room, he can keep the key, and he will not return it unto the other one unless he finishes, he at least enters it once. That is called strict alternation, which means one person will enter, come out, give the lock to him and the key to him, and other person will enter, come out, give the key to him, right? That is why it is called as strict alteration. Now clearly you can understand one thing: when the key is with one person, and if he doesn't want to get into the room, if the other person wants to enter this room, still he cannot enter it because he doesn't have the key. Therefore, obviously, a person who is not interested in getting into the critical section is able to stop the other person, here in this case other process which wants to get into the critical section. Therefore, obviously there is no progress. It is like that dog and horse problem, isn't it? Now dog is guarding this door, but the horse wants to have the grass, right? But dog doesn't want to have the grass, still dog is stopping the horse, isn't it? So again the same problem. So there is no progress here, isn't it? Okay, anyway, let's look at this implementation, and again I'll explain you how the progress. And okay, what about the mutual exclusion? Is mutual exclusion there? Obviously yes. The reason is, it is only one person has the key and only he can enter it, other one can never enter it. Therefore mutual exclusion is definitely guaranteed because of the solution, but only thing is progress is not guaranteed, right? There is no progress. What about bounded waiting? Bounded waiting means, if he wants to enter the critical section, how much time should he wait? He should wait only for one time for him to enter it, right? Which means, while a process which wants to get into the critical section is waiting, the other process cannot enter indefinitely, which means the other process can enter only for one time. Therefore there is a bound on the waiting. What is the bound? You wait for one time for this fellow to enter the room, and once he enters the room and comes out, you can definitely go inside the room, right? So therefore bounded waiting is definitely there. What about architecture neutrality? That we shall see in the implementation, right? Okay, first thing is, it is a software mechanism, which means we don't need any support from the hardware like in the previous interrupts. In interrupts we need the hardware mechanism, right? But here there is no need of hardware, only software mechanism is required, and we don't need any support from the operating system. Everything is implemented in the user mode itself, right? And it is a busy waiting solution. What is busy waiting solution? See, busy waiting solution means, whenever the key is with him, which means he is supposed to get into it, and if this person wants to get into it, he will go and keep on knocking it. Even though it is locked, he will keep on knocking it, right? Therefore it is busy waiting solution, and obviously every busy waiting solution is going to waste CPU time, isn't it? And now it is a two process solution. It can be implemented only for two processes. It cannot be implemented for more than two processes, right? Either you can call the process as P0, P1, or you call them as Pi, Pj. It is simply a two process solution, right? Now for process P0, Okay, watch it now. The code is like this. For process P0 the code is this, and for process P1 the code is this, right? And they both of them will share a global variable turn. It is a global variable turn which will be shared by both the process. And assume that the turn value initially is 0. It can be anything. The turn value initially is 0. What does this turn value say is, this will say whose turn it is to enter into the critical section. If turn value equal to 0, then P0 can enter. If turn value equal to 1, then P1 can enter. Or if turn value equal to I, Pi can enter. If turn value equal to j, Pj can enter, right? So this turn will define who can enter the critical section and who has to wait. Now if turn value equal to 0, who can enter? P0 can enter, right? If turn equal to 1, P0 has to wait and P1 can enter, isn't it? Therefore, now since the turn equal to 0, P1 can enter, but P0 can enter, but P1 has to wait. Just look at the code of P1. As long as you are in non-critical section, no permission is required. If you are not using any shared resource, if there is nothing shared between process, that is called non-critical section. Non-critical section is the part of the code where you access anything which is not shared, right? Which means it is private to your process. So you need not worry, you can access it as at your own will. And now whenever you want to access the critical section, you check whether it is your turn or not. If it is not your turn, which means if turn is not equal to 1, then you wait in a infinite loop. So this is an infinite loop, right? So it will keep on checking. The turn will be 1, isn't it? If the turn is not equal to 1, which means as long as turn is 0, it will keep on waiting here. It is nothing but knocking the door, isn't it? So whenever you schedule this process, and when this process tries to enter the critical section, and if the turn equal to 0, the CPU it will fall in infinite loop in this line, while loop, right? That is why it is busy waiting. And let's see the other one. Now as long as you are in non-critical section, you need not worry about the turn at all. And whenever you want to enter the critical section, now you have to check the turn variable. If turn variable is not equal to 0, you fall in infinite loop, but the turn variable here is 0. That is what we assumed, right? That is the assumption. Now if the turn value equal to 0, it can obviously enter the critical section. Yes, it can enter the critical section and execute it, execute the critical section, and then make the turn equal to 1. Then what happens? The other one, now the turn equal to 1, therefore this one will enter the critical section. So at any time, turn can take either two values, only two values, right? Turn can take either value 0 or 1. If it is 0, P0 can enter it, and if it is 1, P1 can enter it. Therefore there is mutual exclusion. At any time the turn can take only one value, therefore only one process can enter it, even if both of them look at the values at the same time. Earlier it didn't happen because what happened is, with the lock variable, when the lock variable is 0, we are letting both P1 and P2 enter it, and when the lock value is 1, we are not letting anyone enter it. Now that was the problem. Earlier when both of them saw the value of lock as 0, both of them tried to enter. That is why mutual exclusion was not guaranteed there. But here it is not the case. Turn value is going to be either 0 or 1, and either it is 0 or 1, only one process is going to enter it. Therefore mutual exclusion is definitely guaranteed in turn. That is the difference between turn variable and lock variable. Fine. Now mutual exclusion is guaranteed. What about, that is the first one, right? The first condition that any this synchronization mechanism should satisfy is mutual exclusion, satisfied. What is the second condition that any method should satisfy? The second rule is as you remember, the second rule is progress. Progress means if a process doesn't want to enter the critical section, it should not stop the other process from entering it. But then it happens here that even though, let us say, turn equal to 0 and P0 is executing in its non-critical section and it doesn't want to get into critical section, still if P1 wants to get into critical section, it will get blocked here at this line, isn't it? Therefore a process which doesn't want to enter into its critical section is blocking other process which wants to enter into its critical section. So progress is not guaranteed. Fine. And what is the third condition? Bounded waiting. So bounded waiting means a process should not wait forever. Like this, if P0 wants to enter into the critical section, or let us say if P1 wants to enter into the critical section, right, it should not so happen that P naught will enter into the critical section lots of times, and there is no limit on how many times P naught will enter it. If that is the case, then it is called no bounded waiting. But in this solution, it so happened that if P1 wants to enter the critical section, then P naught can enter the critical section in case if it is P naught's turn and if it is not P1's turn. But then once P naught finishes its execution, it should leave the control to P1, which means it should make the turn variable as 1, isn't it? See this. P naught will make the turn variable as 1, which means after its critical section is over, it will give the turn to P1. And similarly, P1 after its critical section is over, it will make the turn to 0, which means it will give the turn to P naught, right? Therefore, P1 is not waiting forever. It is just waiting for P naught to get into the critical section one time, right? And after that, you will get the control, isn't it? P1. Therefore, you need not worry about it at all. So there is bounded waiting. So there is a bound on the waiting. What is the bound? One time. You just let the other process get into the critical section once, then you can use the critical section, isn't it? And then the fourth condition is architecture neutrality, right? So actually we don't need any support from either the software or the hardware, which means we don't have any assumptions about the platform on which we are running it. This can be implemented on any platform. Therefore, it is architecture neutral. So the only problem with this is progress. Progress is not guaranteed, isn't it? So now compared to this lock variable, turn variable is better, but only problem is progress is not good. Later what happens is, later I'll show you one more algorithm that is called Peterson's algorithm. They will use the turn variable itself, but along with this they will use one more variable, right? And that variable will ensure that progress is also guaranteed. So I'll just give a hint here how it is implemented. See, now it is not just enough that you see the turn. Now see this. Using this lock variable, what we did was, if lock variable is 0, both P1 or let us say P0 and P1, they are the two processes. It is any number of processes can use this, but let us say P0 and P1, only two processes are there. Both of them can enter, and if it is 1, no one can enter. And then we use the turn variable. Using the turn variable, if turn is 0, then P0 can enter. If turn is 1, then P1 can enter, right? So here there is a chance that there could not be any mutual exclusion, but here there is a chance that there is mutual exclusion but no progress, right? Now why is there no progress is, if the other process is not interested, still you are stopping one process, even the other process is not interested. Therefore now I want to use a new instead of using one variable, I want to use two variables, like this. Interested of 0 and interested of 1. So if any process wants to get into the critical section, it should say that it is interested, right? Otherwise it should say that it is not interested. So before entering the critical section, you say that you are interested, so that other party will know that, oh, you are interested in entering the critical section, so that will wait, right? Maybe now using this, see here the difference is, till now we are using only one variable, here I use two variables, right? So using two variables, then 0 process P0 will use this and process P1 will use this. So I am even increasing the space at which they will compete. So earlier they are competing at the same value, they are competing at different values. Now they are competing at different variables. Now let's see how to write the solution for this, the synchronization mechanism, and we shall analyze it. Okay. Now P0, as long as it is in non-critical section, fine. And if it wants to enter the critical section, I am talking about the entry section here. It should say that interested of 0, which means the variable for 0, interest of 0 equal to true, which means I am interested in entering it, and then it should even check the other one, right? While interested of 1, the process 1, is equal to true, which means if the other one is also interested, then you should hold, because the other one is actually interested, therefore you should not enter it. Got it? And then after that, entry section, you are going to enter the critical section and then exit. So when you are going to exit, so when you are going to exit, you can write it as you are not interested anymore. Interest of 0 equal to false, right? And similarly in P1 also we could do the same thing, right? In P1 what we can say is, if you are in non-critical section, be there as long as possible, as you wish, and then once you are entering the critical section, if you want to enter the critical section, then what you do is you show your interest, which means interested of 1 equal to, let us say you are interested in entering it, therefore interested of 1 equal to true, and even you check the other one. If other one is interested, the chances are that the other one might be already in the critical section, or it has already shown its interest first, well ahead of you, therefore give it the chance. So while interested of 0 equal to true, then you wait here for the other one to go into the critical section, right? And once the other one comes out of the critical section, it is going to say, you can enter the critical section and then you can say interest of 1 equal to false, right? This is the exit. So this is how you can implement one more synchronization mechanism. Now let's see if mutual exclusion is possible, which means is it possible that both the process can enter the critical section simultaneously. Observe this. Let's see this. Now interested of 0 initially is false, and interested of 1, int is not integer, it is interested, right? And it is false. Now when P0 wants to enter the critical section, now it will make the interested as interest of 0 as true, and it will see that other one is not interested, therefore it can enter the critical section. Let us say P0 is in the critical section, then what happens? Obviously interest of 0 will be true, right? And then now P1 tries to enter the critical section. What it will do is it will make interest of 1 as true, right? But then it will find out here that 0 is already interested, which means the chances are that 0 might already have entered the critical section. In this case it is true, therefore it is going to hold here, it is going to stop there, right? Until what point? Until this one comes out. So you are going to stop P1 at this loop until P0 comes out. Once P0 comes out, it is going to make it as false. Now next time when P1 gets the chance, this while loop will break, because interest of 0 is not true now, it is false, therefore this one will break and it will enter this critical section. The reason is simple. Even if both the process watch the interested first, whoever enters this, and passes this while loop first, right, they are going to get into this. So therefore using this solution, mutual exclusion is guaranteed. What about progress? Mutual exclusion is guaranteed, I'm sure. Just check it, because only one process can enter it at any time. Mutual exclusion will not be guaranteed only if we are letting two processes or more processes enter into the critical section on the same condition, like L equal to 0. But here they are not entering the critical section on the same condition, they are entering the critical section on a different condition. Here we are setting interest of, this is checking interest of 1 and that is checking interest of 0. So both of them are different. See, if you have any doubt, just analyze this a bit more. See, now let us say this is interest of 0 variable and interest of 1 variable. What are the four cases? Interest of 0, both of them can be true, 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 false, false, true, false, false, right? So in this case no one is interested, therefore there is no problem with this. In this case only I1 is interested, therefore who will get the chance? P1. So I1 is having true value, therefore it means that P1 is interested and other one is never interested, therefore P1 can enter the critical section. In this case P2 can enter the critical section, sorry, I0 can enter the critical section, because only that is interested. Who will enter the critical section? The one which has set its interest first and the one which has entered this. But then there is a problem here. Okay, I'll show you that problem. But anyway, here only one process, either P0 will enter or P1 will enter. That depends on who has actually passed this while loop first, isn't it? If P0 has passed the while loop first, these two executed first, then P0 will enter it and P1 will hold there, even though both are having interest rate equal to true. Let's say there is a problem there. I know you got it, but let's hold on. Let's go step by step. First one is mutual exclusion. It is guaranteed. And next one is progress. Progress is guaranteed. The reason is, see, if one process is not interested, it can never stop the other process which is interested. Why? Because we are clearly checking if the other one is interested or not, isn't it? If the other one is not interested, it can never stop it. And then what about the next one? Bounded waiting. What is bounded waiting? Anyway, it is a two process solution, right? So bounded waiting means if one process wants to get into it, the other process, like this, it would happen like this: P0 and then P1 and then P0, something like this, right? So let's see if bounded waiting is possible or not. If P0 wants to get into the critical section, let us say it got blocked, right? Then what happens? The other one which got the permission, see this, let me write it here. See, initially assume that both interest are equal to interest of I0 equal to false and interest of I1 equal to false, right? And P0 wants to enter the critical section, and therefore P0 will make I0 equal to true, right? And then it will enter the critical section, and it is there in the critical section. At that point, P1 wants to enter the critical section, therefore it made I1 equal to true, right? Then what happens? If when it made I1 equal to true, right, and it will get stuck in the while loop. In the while loop it will get stuck. The reason is other one is still interested. So next time P0 comes out of the critical section and then it will make interest equal to false, right? Let us say after some time again P0 only wants to enter the critical section, which means let us say this is in a while loop. It is not just over in one time, it is in a while loop. It will continuously happen, right? And here also everyone wants to enter the critical section continuously. They want to come out of it and again enter it, right? Then let's consider the scenario. P0 came out of the critical section and showed that it is not interested. Again it want to enter it, which means it immediately made I0 equal to true. Now if it wants to enter it, it will just check the interested, right? While interest of other equal to true, yes, interest of other equal to true, therefore this time it is going to wait in a while loop. And now what happens to the other one? P1 again it will try to execute, then again it will be in the while loop showing that other one is interested. Now both of them are interested and both of them will be in the while loop. So it is not just bounded waiting, it is a deadlock. So deadlock is possible. The reason is when both of them show that their interest is true, and both of them get preempted, which means P0 has executed this line, got preempted. Then P1 has executed this line, got preempted. Then P0 will come and check that the other one is interested and it will be in the while loop. And P1 will also come, it will check that the other one is interested and it will be in the while loop. Therefore, there is a deadlock. Whenever there is deadlock, there is no bounded waiting. Isn't it? Deadlock is more severe than bounded waiting. The process are going to wait forever. They are never going to get out of it. So the problem with this is deadlock. Even though there is no assumption about the architecture, it is architecture neutral. Fine. The problem with this one is deadlock. So progress is guaranteed here, but we came across the problem of deadlock, right? So if you look at the turn variable, mutual exclusion is guaranteed, but progress is not guaranteed. But bounded waiting is guaranteed. Is bounded waiting guaranteed? Yes. Bounded waiting is guaranteed, and architecture neutrality is guaranteed. Now, individually, interested variable is having some problem, and turn variable is having some problem, right? Now, what Peterson did is he combined both these concepts, both the turn and the interested.